Hi there, welcome to this presentation. My name is Nathan Ellis, and today I'm going to talk to you about the emerging field of hybrid switched capacitor power converter design, and more specifically, a recently published topology coined the dual inductor hybrid, or DIH topology. I'll talk you through its origins and describe some of the challenges that researchers have had to face in order to get this topology to function well. Then, as part of this work, I'm going to demonstrate a modified clocking scheme that greatly enhances the degree to which these converters can utilize the energy density of their flying capacitors. But first, we're going to talk a little about the rapidly developing industry of data centers, an application space where these types of advanced converter topologies are beginning to find use. In 2016, a report was published declaring that data center power consumption has been increasing at a rapid rate since the early 2000s. It was documented that many of these facilities expended large amounts of energy simply on cooling and power distribution, while ideally we would like most of the energy to be used to crunch through ones and zeros within the actual product, the servers themselves. As a result, today, companies like Microsoft, Google, and Amazon have been pushing for more and more streamlined data solutions that cut cost by improving on their system's efficiency or effectiveness. As a result, rather than seeing a continual climb in energy consumption as demand increases, we've been able to slow our consumption considerably with a shift to hyperscale facilities and existing best practices projected to improve things even more. One key element of these systems are the power converters that allow high voltage transmission throughout the facility to be followed by low voltage data processing. Ideally, this step down in voltage would occur as close to the load as possible to preserve our high voltage transmission efficiency. As such, with the present day shift towards 48 volt and higher bus architectures, there is a strong incentive to develop highly compact, high efficiency, and low cost 48 volt to point of load converters that can be situated directly on the server card. Now, this transition has been softened by the development of 48 to 12 volt intermediary bus converters that support legacy loads, but in this presentation we are going to focus on the more ambitious direct 48 point of load topologies. To achieve this, both research and industry have been taking a very close look at a family of converters termed hybrid switched capacitor converters. These converters effectively utilize the very high energy density of capacitors to perform the majority of the voltage conversion, but which also use some small amount of inductance to overcome the pitfalls associated with purely capacitor-based designs. The figures shown here are from work done by Zichao Ye here at Berkeley, where it is very clear to see the difference in passive component volume as you make an apples-to-apples comparison between a buck converter, a switched capacitor converter, and a hybrid switched capacitor converter. Note that despite its minimal size, the hybrid approach still achieves the highest efficiency overall. To this end, one very promising new topology is the DIH converter. I'll talk about its history in a moment, but to summarize, this topology has many attributes that make it very well suited for direct point-of-load conversion. For example, it has been proven to achieve very high power densities in practice while making very good use of both its switches and passive components. The key challenges associated with this design are those of capacitor sizing and orchestrating the switches in a way that gives optimal performance. In tracing the evolution towards this topology, we can go back to a paper published by Muller and Kimball in 2015, where we see an underlying switch structure that is essentially identical. However, this design was operated as a step-up variant using diodes, and so the authors did not need to concern themselves with the complexity of a fully synchronous solution. Additionally, rather than using a Dickson-type capacitor network, this design used a Cockcroft-Walton structure. If you would like to watch a discussion on the nuanced differences between Cockcroft-Walton and Dickson-type capacitor networks, then please see the following link. But moving forward, the modern-day dual-inductor hybrid was published in 2018 by Han-Fuck Lei's team at UC San Diego. These guys demonstrated two different variations on this topology, one focusing on odd-order capacitor networks and the other on even-order networks. To understand why even and odd networks are treated differently, first we must do a little bit of analysis. Taking an even sixth order network as an example, here we can draw out our two primary operational phases. shown here as phase 1 and phase 2. At this point, we can apply some straightforward charge flow analysis to deduce how charge flows through the converter during each phase. If we assume that both inductors have small current ripple, phases are of the same duration, and that energy is conserved, we can fairly easily calculate the conversion ratio by comparing charge in versus charge out. In this case, for n equals 6, we have a 12-to-1 converter. Additionally, if we want to regulate the output, we can easily add 2 additional phases as shown. Similar to a basic buck converter, these extra phases serve to reduce the average driving voltage on the inductors, and subsequently the output voltage is reduced. By varying the duration of these extra phases with respect to the original phase 1 and phase 2, we can successfully modify our conversion ratio. Now, this sounds all well and good. However, there is a problem here. The problem being that the capacitor network is actually not soft charged. At first, this is not easy to see, so let's briefly consider the previous charge flow analysis. If, for example, we now set all capacitors equal, we can use Q equals CV to determine the voltage ripple that occurs across a branch during a given phase. For example, the highlighted branch conducts a charge quantity Q while having an effective lumped series capacitance of C/2. As a result, this branch wishes to express the following voltage ripple. Conversely, taking a look at the single capacitor branch below it, we see that this branch also conducts a single charge quantity Q during the same phase. As a result, this branch only wishes to see half the voltage ripple of the branch above it. Since both branches are connected in parallel and must express the same voltage, this inconsistency will result in transient inrush currents and hard charging losses. Now, we can attempt to modify the voltage ripple behavior by modifying the values of the fly capacitors. For example, here we could half our fly capacitance in an attempt to match its desired ripple to that of the branch above it, but this has unintended consequences for the alternate phase 2, and it turns out that for this even order network, there is no set of capacitor values that avoids this inequality. This is not the case for odd order networks on the left, where it was shown that if you choose specific capacitor values, you can actually achieve complete soft charging fairly nicely. However, as these odd order networks go higher and higher, we see that the capacitor values required to avoid hard charging balloons upwards very quickly, leading to relatively poor energy density utilization in practice. Conversely, although no specific sizing exists for even order networks, the San Diego team did recognize that they could employ a recently published technique termed split phase switching to resolve this. Next, we will go into a little more detail explaining this technique, but you can begin to think of split phase switching as oftentimes being an active imitation of what diodes do naturally, that is, to only turn on upon realization of zero voltage switching conditions. Although, in the next section, we will expand this definition to also encompass the strategic turning off of switches such that all voltage constraints are satisfied come the subsequent switching phase. But for now, let us look at the solution proposed in this 2018 work. Here, it was demonstrated that both phase 1 and phase 2 could each be split into subphases A and B as shown. Since some branches want to change by a larger amount than other branches by our earlier reasoning, what we can do is allow the branches that wish to change by the greatest amount to conduct for the full phase duration. But for branches that wish to change by less, we only implement these branches for part of the phase duration, hence the term split phase. For example, here you can see that one of the capacitors is only included in the power flow path during phase 1B, whereas all other capacitors conduct for phases 1A and B. The question then becomes, at what point in time should we transition from phase 1A to 1B, or when should this capacitor be included? To help visualize this, we are going to take a closer look at how capacitor voltages change with time as a phase progresses from start to finish. Throughout this phase, inductor L1 is sucking charge out of the left side of the circuit, decreasing the voltage across S1 as the phase progresses. Here you can also see that I've annotated each of the fly capacitors with a DC bias plus or minus some voltage ripple delta. Note that since all of the capacitors have been set equal in this example, and since all of the capacitors conduct equal charge, this implies that all of the deltas on each capacitor are also equal. As such, from start to finish, each capacitor should undergo a twice delta swing, while series connected branches should express a 4 delta swing. Since the series connected branches desire the largest voltage ripple, they are connected for the full duration and define the maximum deviation of VDS1. So it makes sense that we should only include our single capacitor branch after a 2 delta swing has elapsed and while there still remains an additional 2 delta swing for it to partake in. This is the moment at which we switch in our fly capacitor, where it then continues with the others until the end of the phase. In this way, we have successfully soft charged all of our fly capacitors with no jarring and abrupt hard charging transitions. But there is still a limitation here. If we take a closer look at switch S3 in this example, we see that before the splitting event, this switch was subject to a reverse bias. The San Diego group recognized this and described that in practice, the voltage ripple across the fly capacitors must be kept very small, less than the reverse conduction threshold of the switches, ideally 0 volts, but in reality about half a volt in silicon and a little higher in gallium nitride. So if we now take a look at their published waveforms, we see that the voltage ripple on all fly capacitors is greatly constrained to be less than 1 volt. Now, please do note that by keeping your capacitor ripple very small, you are not using its full energy transfer capability. In fact, you are stifling it. If you want to use your capacitors most effectively, you really want to operate them with large voltage ripple. So this is a problem. However, in this work, we propose a simple solution. By delicately reordering the intended phase progression, we are able to eliminate these reverse bias conditions and greatly enhance the allowable voltage ripple across our fly capacitors. To observe the intuition behind this, let us redraw our time progression for phase 1. In this new scenario, we begin the phase with all fly capacitors connected. Since our single capacitor branch still only requires a 2 delta swing, in this case it must be omitted part of the way through the phase. After this time, we see that S3 incurs a positive forward voltage bias, removing the possibility of any reverse conduction and allowing our fly capacitor voltage ripple to be greatly increased. Dissimilar to the previous method where the splitting event could be actively sensed by the bias across S3 going to 0 volts, here we must rely on calculated timing durations or indirect measurements, as any timing errors here won't incur hard charging effects until the start of the next phase. Fortunately, calculating the time at which S3 needs to be turned off is fairly straightforward, and if you continue to make the assumption of 0 inductor current ripple, you can arrive at the solution pretty quickly. Please see the paper for details. But the key takeaway here is that for split phase switching in general, you usually want to switch capacitors into the power path in step-up converters, whereas in step-down topologies, you may want to look at sequentially removing capacitors as the phase progresses. As a quick side note, if you're struggling to visualize the step-down scenario, then one good tip I would recommend is that you first design a step-up converter, where diode type 0 voltage switching is used, and then simply perform a time reversal and watch as the charge flows back down to the input as we travel backwards in time. This should give you the correct phase sequence. In order to demonstrate this subtle shift in switch sequencing, here we present a constructed hardware prototype. This design is very similar to that demonstrated in 2018, but what we are going to do here is reorchestrate our split phase control as previously described. In this demonstration, we opted to use very large inductors such that our result would match our theoretical predictions. But of course, in practice, you may wish to opt for a more performance-optimized design. As a result, the inductors dominate our converter volume as shown. To deliver power to each of our high-side gate drivers, we used a standard cascading bootstrap. Efficiency curves were taken at a number of different output voltages and at switching frequencies of 750 kHz and 300 kHz, with most peak efficiencies well above 90%. At heavy load, most of our losses are conduction-based, with temperatures never exceeding 80 degrees Celsius. Next, let's take a look at some voltage waveforms. Here I am showing you the measured voltage stress on all 8 switches. Do observe that at no point does any switch undergo a reverse bias, with split phase switches, including S3, seeing a positive increase in blocking voltage once the phase splitting occurs. If we then take a look at our fly capacitor voltages, we see that during phase 1, the voltage on C1 stops changing once we transition to phase 1B as we remove it from the power path. Conversely, all the remaining capacitors that are contained within series connected branches continue to change until the end of the phase. Now, importantly, notice that here our fly capacitors are operating with a very large voltage ripple, over a full order of magnitude larger than that previously demonstrated. This indicates highly effective use of these energy transfer elements, with much smaller capacitors being required in practice. Additionally, all capacitors see smooth and continuous voltage transitions, verifying that they are all being soft charged with high efficiency. Finally, we compare this converter with several recently published 48-volt to point-of-load solutions and take a look at a number of comparative properties. Despite its oversized inductors, used here to keep inductor current ripple small and simplify our analysis, this design actually performs pretty well, with measured power densities and efficiencies on par with recent state-of-the-art. As such, we expect further improved metrics in a design that is optimized for power density. If you would like to take a look at a highly optimized converter presented at this year's ECCE, I would refer you to my colleague Yicheng Zhu's presentation at the following session description. So to conclude, there are still strong incentives to improve upon converter solutions that perform medium to large conversion ratios, particularly in integrated power delivery and processing systems such as data centers, but certainly also in electric vehicle, aviation, and space applications, for example. In this work, we've demonstrated a modified split-phase clocking scheme that greatly improves the passive utilization of fly capacitors within a state-of-the-art hybrid switched capacitor topology. Despite having greatly oversized inductors to better approximate ideal derivations and analysis, our prototype is still highly competitive with recent work. If you have any questions or comments on the content presented here today, please don't hesitate to reach out. Thank you.